So, we discussed size of the nucleus, we discussed mass of the nucleus, and now the next phase is forces within the nucleus. So, as you know, nucleus is made of protons and neutrons, which collectively we call nucleons. So, what are the forces between these nucleons which finally binds the nucleus? That is the next phase. So, first let us see what are nucleons, protons and neutrons. Are they structureless particles? And the answer is no, they are not structureless particles. They do have structures inside. And how one reveals that structure? In almost the same way as this alpha particle scattering reveals the structure within an atom. So, the question which was solved using that alpha particle scattering experiment was what is there inside the atom, and the scattering experiment revealed that most of it is empty, most of the atom is empty, and then you have a nucleus, very small volume nucleus with strongly deflected alpha particles. Similar question is what is there inside a proton or what is there inside a neutron, and the technique is also similar. Send highly energetic particle in it and see what this particle does to itself, how it scatters. Look at the angular distribution of the scattered particles. So, high energy electrons, something like giga electron volt energies. So, that the de Broglie wavelength is much smaller than a femtometer, say 1 by 20 of a femtometer or so. So, these electrons when sent into protons or neutrons, then they are scattered and their angular distribution reveals that yes, inside proton also you have structure, or inside neutron also you have structure. Not only structure, you have something like point particles inside. So, which today we very well know that it is quark structure. A proton is made of 3 quarks, a neutron is made of 3 quarks. Okay. So, the entire matter in the current understanding, the entire matter of the universe is made from 2 kinds of particles, and they are quarks and leptons, and these nucleons, they are made of quarks. Quarks themselves are of 6 varieties, 6 kind, that is called up quark, then down quark, strange quarks, charm quarks, then top and bottom. So, 6 flavors of quark, and they have antiparticles also, anti-quarks also. So, you will have 6 plus 6, 12 kinds of 12 different kinds of quarks, and then you have leptons, and these quark and leptons make the entire universe. Electron, your muon, or this neutrino, these are leptons, and these nucleons are made from quarks. Pi mesons, they are made from quarks, and these quarks which were proposed to make a nice theory in something like 1964, and later on people experimentalists searched for this quark inside the protons and neutrons, and the experimental evidence started coming 1968 or so. So, all these 6 are now experimentally revealed or studied. So, and they have fractional charges. The interesting thing is they have fractional charges. This so called up quark has 2 by 3 e electronic charge. This charm, this also is 2 by 3 e, and this top, this also is 2 by 3 e, and the other 3 are minus 1 by 3 e. So, minus 1 by 3 e and minus 1 by 3 e. These are the fractional charges. Anti-quarks will have opposite charges. Okay. So, a proton is made from U, U and D. So, you have 2 U quarks, that will make it 4 by 3 E, and one down quark, that is minus 1 by 3 E, and the total will be plus E, right. So, the total charge will be 2 by 3 E plus 2 by 3 E and minus 1 by 3 E, that is plus E. Whereas, a neutron is made from 2 down quarks and 1 up quark. So, that will be minus 1 by 3 E, minus 1 by 3 E and plus 2 by 3 E, and that will be 0. So, neutron does not have a charge. This statement is to be understood in this context. The total charge on the neutron is 0, but it is not that there is no charge in the neutron. You have 3 charges in the neutron, minus 1 by 3, minus 1 by 3 and plus 2 by 3 E. Total is 0. Similarly, this total is 1 unit of electronic charge, but that 1 unit of electronic charge comes from 3 parts, 2 by 3 E, 2 by 3 E and 1 by 3 E. Okay. So, that is how, and the forces that originate between nucleons, they are essentially forces between these quarks. Okay. And what is the kind of force? This we call strong force. Strong force, nuclear force is strong force. So, that is you have gravitational force, or gravitational interaction, and that comes from mass. If there is mass, there is gravitational interaction. Similarly, this electromagnetic interaction, from where it is coming? Right, Coulomb force comes from charge. If you have charges, you have electromagnetic interactions. Similarly, once you come for the strong force, what is that quantity here? That quantity is called color charge or color. The technical name given is color. Right. So, quarks have color like mass. Color, that does not mean that it is colorful. It is not that color. If you shine a light, then that light will certain wavelength will be reflected, certain wavelength. It is not that color. It is not that color. It is just like mass is an intrinsic property. Charge is intrinsic property. Similarly, this color is intrinsic property. The name color is given, and the 3 quarks here have different colors, and the name of these different colors are also given as red, green, blue, RGB. Okay, red, green, blue. So, red, green and blue, and when you add all these 3, it becomes 0. Right. So, different quarks, the 3 quarks UUD or UDD inside a proton or inside a neutron, they have different colors. And total color is 0. So, the strong force is because of this color charge on the quarks. Each quark has a color, but then all 3 quarks in a nucleon taken together, the total color is 0. So, how there is a strong interaction between 2 nucleons? Because on each of the nucleon the total color is 0, and the strong force comes only if you have color. Right. So, your situation is something like molecules. You know, each molecule by itself is neutral, charge neutral. In a molecule you have atoms, you have nuclei, positively charged nuclei, then you have electrons, and the molecule as a whole, water molecule for example H2O is neutral. But then in a water mass, in a liquid, water, liquid, all these molecules interact with each other. They do exert forces, electromagnetic forces. Otherwise, if each molecule is free, not interacting with anyone, it will not be in a particular volume. How it is maintaining that volume? It is maintaining that particular volume, they are confined into that space because molecules are attracting each other and they are interacting. Okay. In a gas, the interaction is much less, and therefore, the molecules can go anywhere, whatever volume you provide, the molecules will spread into this entire volume, right. But in liquid or in solid, the molecular attraction is much stronger than in gases. In gases also there is some molecular interaction, that is why that ideal gas equation is not valid in many cases, and you go for that van der Waals equation of state and this and that. So, molecular interactions are in gases also, but liquid is it is more, and solid it is even more. So, neutral molecules can also interact with each other through electromagnetic interactions, but then this electromagnetic interaction is effective only if the molecules are close to each other. At that length scales, it is again a short range force. If you have two charged particles at say 10 angstroms distance, two charged particles, there is considerable electromagnetic force. But if you have two neutral molecules at 10 angstrom distance, the interaction will be much weaker, because this is neutral, this is neutral. So, no Q1, no Q2, Coulomb force simply will not give. But if the molecules are close enough, so that the internal structure of charge distribution is now visible, the molecule starts feeling the distribution. If it is looking only at the total charge, then the total charge is 0, and that will happen if the molecular size is small as compared to the separation between the two molecules. Okay. If two molecules are this distance apart, and then the size of the molecule is small, it is like point particle. So, the total charge is 0, total charge is 0. But if the separation between them is of the same order as the charge distribution, then if we have some positive charge at this side, negative charges that side, and there is some distribution, then that distribution will be felt here, that okay, although the total is 0, but this positive is closer to me, that negative is farther away from me, and so on. So, there will be some what you can call residual forces, although the total charge is 0, but still you will have some residual forces, and that is this molecular forces. So, at that scale molecular forces are also short range, and molecular potential, if you remember, is generally shown in books like this. This kind of diagram you have seen for molecular potential energy. So, that is short range. This defines the range, something like this. This distance defines the range, and this defines the strength of the attractive potential. This depth defines the strength, and this defines the range beyond which the attraction will be very small. So, similarly here, although the total color on the two nucleons is 0, but then if the separation is small and if that same order as the distribution inside the nucleon, then you will have some color interaction, just like the molecules had some electromagnetic interaction even if the total charge on each of them was 0. Similarly, here the total color charge or color on each of the nucleons is 0, but if these two nucleons are close enough, so that the distribution of UUD or UDD, that distribution, the size of that distribution and the separation between these two is of the same order, then that color interaction will start giving some results. So, the nucleon force originates from here. It has to be a short range, because it is color neutral, it is an interaction between color neutral entities. So, it has to be short range, you have to bring the nucleons close enough, so that this color interaction can be significant, right. So, that is why it is short range. So, not going into this particle physics domain too much, we will just take that okay, nucleons do have some strong interactions which we called nuclear force or nuclear interactions, and will correspond to some kind of potential energy of this type. You will have some depth of the potential giving the strength of this nuclear interaction, and you will have range. So, the shape, what functional form, all those details are there. To study nuclear forces means to study the shape of this potential, the functional form of this potential, and other things, the details of these potentials. So, with this much of basics why there is a nuclear force between the nucleon, I start the study with simplest possible nucleon-nucleon interaction case, where you have just two nucleons and a bound system. That is the simplest thing to study, two nucleons and bound system, and that is Deuteron. Deuteron is a nucleus of two nucleons, and that is one proton and one neutron. So, you write it 2 H 1 1. So, total capital A is 2, then Z is 1 and N is 1, and since Z is 1 proton, so it is hydrogen, it is a nucleus of hydrogen. So, you write it in this way, it is just a combination of neutron and proton. This is the only two nucleon nucleus. You do not have a nucleus of two protons, it is not a bound system. You do not have a nucleus of two neutrons, it is not a bound system, but you have this one neutron and one proton nucleus, it is a bound system. So, experiments have already given some parameters, and few parameters that we can list here is, one is binding energy. Binding energy, as you know, can be obtained from measured atomic masses very accurately, and for this Deuteron system the binding energy turns out to be 2.225 MeV. So, it is a weakly bound system. Can you see why it is a weakly, why do I say that it is a weakly bound system? The binding energy is 2.225 MeV, and there are two nucleons. So, what is binding energy per nucleon? 1.1 MeV. If you remember that binding energy per nucleon curve as a function of A, most of the nuclei have binding energy per nucleon about 7 to 8 MeVs. Remember that? Okay. Most of the nuclei in that whole chart, it is maximum around iron nickel in between, and then it slowly decreases, but mostly most of them will be around somewhere around 7 MeV to 8 MeV binding energy per nucleon, and here the binding energy per nucleon is 1.1. There are two nucleons and the total binding energy is this. So, it is 1.11 MeV or so. So, it is a weakly bound system in that context, right. Then the range of this interaction, that also one can work out from the measured radius. The radius can be measured through different experiments. So, that radius tells that okay, this is almost the range of that interaction. That is from the experiments we get this as 2.1 femtometers. What is the strength of this nuclear interactions? So, this is an area where a lot of experiments have been done, and through large number of experiments people have come out with the shape of or the functional form of nucleon interaction potential, but that happens to be a really complicated function. It is not simple to write. Okay. So, what our first scheme will be to approximate this nucleon interaction potential by a very simple form which we can mathematically handle easily, and find out the parameters, strength of the potential. How strong is nucleon potential? I said that is given by the depth of that potential well which is binding it. Okay. So, we assume simplest kind of potential form, and that is, so assume not that there is a great theory behind the expression that I am writing, it is an assumption. So, assume square well potential. Square well potential which depends only on r, the separation between the two nucleons. So, as a function of r, we say that the potential is like this. It is this is r equal to 0 and this is r equal to r naught, and this is the potential. Right, this is square well potential. It is a well like structure. On horizontal axis you have separation between the two nucleons, and on vertical axis you have potential energy of those two nucleons, and it says that beyond r equal to r naught, this side, the potential energy is 0. It is unbound system. When two nucleons are separated from each other, not in a bound system, that energy is 0. So, this is that part, and this is the range in which the nuclear potential is effective, and this is the strength. How deep is the potential? This will be measured in mega electron volts. So, how deep is the potential? So, if the potential is deeper, that means the interaction is stronger. Okay. So, this is V naught, this point is minus V naught, right. So, this is, so r less than 0, no question, separation between the two nucleons cannot be negative. So, it starts from r equal to 0 and up to r equal to r naught, the potential, when we say potential, it is potential energy, right. Quantum physicists always call it potential, but it is measured in energy units. So, from here to here the potential is minus V naught, and then here it is 0. It is a oversimplified form, but to get the idea of how strong is this potential, for example, molecular potential energy, if you plot, the depth will be few electron volts. Here it will be in mega electron volts, but how many? 5 mega electron volts or 50 mega electron volts or 500 mega electron volts. What is the strength of that potential? That we can obtain using these information. So, what we will do? Assuming this square well potential and assuming that the range is given by this 2.1 femtometer and that the binding energy is 2.225 MeV, we will find this depth V naught. And what is this binding energy in this diagram? What does it mean? That means the total energy E of the particle is minus 2.225 MeV. So, total energy of the particle is minus, I do not know how much is this V naught, how many mega electron volts is V naught. So, depending on where it is, it will have some, you can draw a line here and say that this is the energy of the deuteron, minus 2.225 Why minus? Because if you give this much of energy, if you pump this much of energy, the total energy will become 0, and total energy becoming 0 means the two things have gone apart, the two nucleons have gone apart, the deuteron is broken, and that is the meaning of binding energy. right. That is the meaning of binding energy. It is bound by this much energy. If you supply this much energy, you can break this nucleus into its constituents. So, binding energy is 2.225 MeV, means that the total energy is minus 2.225 MeV. This is not the mass energy, remember. It is coming from the nuclear interaction, the kinetic energy of the particle, the relative kinetic energy, of course, I will talk about that, and the potential energy, nuclear potential energy. So, it is coming from mass energy is not included, mass of proton and neutron is different, 938 MeV and so on, right. So, the energy is this, this depth will be more than that, right. You know how to solve it, quantum mechanics. If a square well potential is there of some depth V naught, it will allow you bound states at certain energies. The lowest energy, ground state energy, then first excited state and second excited state and so on. In Deuteron, you do not have any excited states, that is also an observation, no excited states. So, just one bound state, single bound state at this energy and no excited states. So, this is also the ground state or lowest energy state. So, I believe you must have done courses on quantum mechanics for square well potential, how to get that bound state energy levels and so on. I will just go through those steps, but not in much greater details, but still this is a 3-dimensional square well potential, right. R equal to 0 and then R, as R changes, R increases, you have this attractive potential in all directions, right, and then when R is greater than R naught, then the potential energy is 0. So, it is a kind of a spherical volume in of radius R naught. So, it is central potential, the assumed potential. I am not telling that the nuclear potential is a central potential, but the assumed potential is a central potential. The assumed potential is a central potential. Central potential means this potential energy V does not depend on theta phi, it only depends on R. So, that is, we have assumed a central potential. Now, what is this small r? All equations we want to write is in terms of this small r. This small r is separation between the two particles. So, we are working in what we call relative coordinate systems. For two particle system, if you have two particles, and here is your origin and axis, then you can write the position vectors of the two particles as r1 and r2, right. But then this vector, this is the relative position vector, r is equal to r2 minus r1. This is relative position vector. This potential energy and energy states, energy levels, they all correspond to this relative position vector. As a whole, this whole particle, 2 nucleon particle, can go from here, 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 here. The deuteron can go from here, there, it can have some kinetic energy, it can have linear momentum, the whole deuteron. That is not coming in this potential. This potential is for the interaction between the two nucleons wherever they are. The deuteron can be here, or deuteron can be here, or deuteron can be there. So, this center of mass motion or motion of deuteron as a whole, that is not covered here, and we do not need that. This energy is coming from the interaction. So, one relative to the other, that is giving me this energy. So, we have to work with this vector. So, when I am writing here V as a function of r, and this r here, it is, we are talking of this separation only. But if you are using this relative position vector, which is position of the second particle as seen from the first particle. So, where are you placing your origin? You are placing your origin on the first particle. If you want to use this vector r and write your equations of motion in terms of this r2 minus r1. So, it is this vector. So, you are looking at the position of second particle from the first particle. So, in a sense you are using a non-inertial frame, because this particle itself is will have acceleration if I use classical physics terms, right, because of force from the second particle, this is accelerated, and I am putting my observer here and looking at the second particle from the first particle. So, I am using non-inertial frame. So, I must use some correction terms, and it turns out that all those correction terms can be taken care of with the simple change that mass that you use in place of, this is mass m1, this is mass m2, and if you use a mass m1 m2 by m1 plus m2, which is called reduced mass, of the two particle system, so if you use this mass m, then all that correction is taken care of. So, as if you are working from an inertial frame, there is origin and there is only single particle of mass small m, which is the reduced mass, okay, which is the reduced mass, and then use all the standard equations, standard formula, standard method, you get the right answers to all these energies and everything for this relative motion. Okay. So, with that background, let us start that so called standard method, and the standard method is that if you have a central potential, the energy eigen functions are easy to write. First, let us write the energy eigen equations, and that is called time independent. How do you get energy? From time independent Schrodinger equation. And that is Hamiltonian, and then you have this wave function and is equal to E and psi. And the Hamiltonian here is minus h cross square by 2 m, this m is the reduced mass, and then del square. So, this becomes the kinetic energy operator, and then potential energy operator is just multiplication by this V, and this whole thing operating on psi r gives E times psi r, right. And if it is a central potential where the potential energy term V as a function of position vector r does not depend on theta phi, it is spherically symmetric, all directions it is same, right, spherically symmetric system. In that case, this wave function very nicely splits into two parts, and the psi r can be written as a radial part depending only on r, not theta phi. So, you have some function r which we write as phi, let me write phi r, not r vector, only r, and then the theta phi part are just standard y lm theta phi, and these y lm theta phi are called, what are they called? Spherical harmonics. Standard expressions, L can be 0, 1, 2, so on, and this m, let me write ml because m I am using for reduced mass. So, 0 plus minus 1 and so on up to plus minus L. So, ml depends, the limit of ml depends on L. With these integral values of L and ml, this spherical harmonics have standard expressions, and whatever is the central potential, once it is a central potential, once you know that your potential energy does not depend on theta phi, it depends only on r. The theta phi part is fixed, it is only the r part which will depend on the actual shape of the potential, right. So, it is this, and this part, this radial part, this decides the energy, theta phi part are anyway fixed. So, it is only this which decides the energy, and this phi r, if you write this phi r as some other function of r divided by r, in other words you define this u r as r times phi r, okay. Then in terms of this u r, your equation becomes very simple. It is minus h cross square by 2 m d 2 u by dr square plus v r plus L L plus 1 h cross square by 2 m r square u is a function of r, remember. So, u multiplied by u, that is equal to E u, right. So, it reduces to one dimensional equations, one variable equation. U is just a function of r only, not theta phi, right. This u is a function of r only, because theta phi part are here. So, that is why you do not have any partial derivative, total derivative, okay. So, this is the equation which we have to solve. Now, since deuteron has only one energy, that is the lowest energy, okay. Now, in this equation you can look at this L L plus 1 term. L can be 0 or L can be 1 or L can be 2, but as you increase the value of L, this is going to contribute positive in energy, right. So, the lowest energy is obtained in any central potential, the lowest energy is obtained when L is 0. So, for our case of deuteron, where we are looking for that lowest energy, in fact, there is only one energy and therefore, it has to be lowest, this L will be 0. It is under our assumption, I remind you again and again, right. L equal to 0 is because we are working with central potential, and it is central potential, that is our assumption for just getting an idea of the strength of this potential. The actual potential in fact is not central, and that is why I am telling it again and again, the actual potential does have some non-central part also, but assuming central potential, assuming this is square well shape, we are doing all this analysis and this L should be 0. Now, if L is 0, now ML is 0, and then this spherical harmonic is just a constant, just a constant, no theta phi dependence, y 0 0, y 0 0 is just a constant, square root of 1 by 4 pi. So, the wave function is only given by that r part, right, and the equation is minus h cross square by 2 m d 2 u dr square, so that is this term, plus V r into u. So, plus V as a function of r into u at L is 0, so, and this is equal to E u. Now, there are certain conditions on the wave function called boundary conditions, and what are they? The wave functions psi should be continuous everywhere, should be finite everywhere, nowhere this should go to infinity, should be square integrable and the derivative should be continuous. At any point the space derivative should be continuous. A slope should be continuous. The wave function does not have cusps, the wave function does not have those corners, it is always a smooth function. So, the derivative is constant, is continuous. So, these are the conditions. Square integrable means that psi square and the volume element you integrate over the entire space, that should be finite. We normalize it to make it 1, but it should be finite, only then you can normalize. Now, in terms of u, this will become u square dr equal to finite, r going from 0 to infinity. In terms of u, it will be du dr becoming continuous. Psi continuous means u continuous, and all this u continuous, u finite, u square integrable and all those things, right. Theta phi part is anyway constant. So, let us work out. You have your potential is of this type, this is r equal to r naught here, this side is r, this side is v, this point is 0 and this point is minus v naught. So, you have two regions, this V r, this potential energy term is different if r is less than r naught and is different if r is greater than r naught. So, you have two regions, one region is from 0 to r naught and the second region is r naught to infinity. So, for r less than r naught, V is minus V naught, right. So, your equation is minus h cross square by 2 m d2 u dr square and minus V, V is minus V naught times u is equal to E u, or d2 u dr square is equal to what? Let me write minus h cross square by 2 m d2 u dr square is V naught plus E times u, right. So, d2 u dr square is minus 2 m V naught plus E over h cross square times u, correct. And this thing if you write as k square, then it becomes d2 u dr square is equal to minus k square u, where k is square root of 2 m V naught plus E by h cross square. It is a real quantity. The potential I had written is minus V naught. So, that means this V naught is a positive quantity, that V naught is here. This E is negative quantity, this E is the energy of the deuteron that is going to come. So, E is negative, but then the magnitude of E is smaller than the magnitude of V naught. So, V naught plus E will be positive. So, this will be a real quantity. d2 u dr square is equal to minus k square u. You know what is u as a function of r from this equation? So, u as a function of r from here, for this is for region 1, remember, r less than r naught. U as a function of r is a, so you can write u1 a sin kr plus b cos kr, is like that simple harmonic oscillations. then you can apply your conditions. Psi should be continuous everywhere, that means u should be continuous everywhere, and psi should be finite everywhere. Therefore, this has to be finite everywhere. And what was u? ur by r, that was phi r, correct, the r part of the wave function, and then you had theta phi part, which in our case is just a constant. That means ur is equal to r times phi r. So, if phi is finite everywhere, then at r equal to 0, this ur should be 0, right. Phi is finite everywhere. So, at r equal to 0, this ur should be 0. So, it tells me that at r equal to 0, this u r has to be 0, and if you put it here 0 here, u is 0, and r, you put r equal to 0, this is anyway 0 and this is 1, cos of k r is 1. So, it is just b. So, it gives me b equal to 0, and hence u 1 r is just a sin k r. Now, look at the other region, r greater than r naught. So, if you do for r greater than r naught a similar analysis as you had done here. So, for r greater than r naught, what will happen? V is 0. For r greater than r naught, potential energy term is 0. So, this V is 0, and hence your equation is minus h cross square by 2 m d2u dr square is equal to EU. Thus, V is 0, and therefore, d2u dr square is equal to minus 2 m E by h cross square and u, and this you can write as gamma square u, where gamma is square root of minus 2 m E over h cross square. Is this gamma real or it is imaginary? Gamma is defined, this I am writing as gamma square u. So, this whole thing I am writing with this minus sign, I am writing as gamma square, and therefore, gamma is the square root of this. So, gamma is the square root of minus 2 m E by h cross square. Now, this gamma is real or it is imaginary? It is real, because this E, total energy E, is negative. We know that this total energy E is here. Look at this diagram, the total energy E is here. This is equal to 0, this is your 0 level, it is a bound system. So, if I start with E equal to 0 for separated nucleons, the bound system will have lower energy, it is negative. So, E is minus 2.225 MeV, right. E is negative, and therefore, this whole thing is positive and is square root of a positive quantity. So, it is real. So, that is why I have written in this fashion, k is also real and gamma is also real. So, this is it. Now, this equation is also I am sure you must be knowing, d2u dr square equal to gamma square u, with gamma as real quantity, gamma square as positive quantity, and this is u second region will be some constant e to the power gamma r and plus some other constant e to the power minus gamma r. Exponential, right, exponential. If this quantity was negative as in the first case, it was oscillating sine cosine, and if this quantity is positive, then it is not oscillating, it is exponential, decay or rise. But then your wave function has to be square integrable, and wave function has to be square integrable will mean that u square dr integration has to be finite. So, if you think of very large values of r, this u should go to 0, As r goes to infinity, this u should go to 0, otherwise u square integration will not be finite, right. So, it has to die down, so that the whole area is finite. If even at r equal to infinity this function is not becoming 0, so it will keep on giving you areas and the total area will not be finite. So, this u must become 0 when r is very large, right. So, look at these two terms, r equal to, let us say r equal to infinity, then here it is e to the power minus gamma r. You can always take positive values because you have both gamma and minus gamma. So, taking gamma positive, this is decaying, this is going to 0 and this is rising and this is going to infinity. As r goes to infinity, this term will go to infinity and this term will go to 0, and since u must go to 0 as r tends to infinity, this term should be absent, and that will happen when this c is 0, right. So, at r going to infinity, u must go to 0 and that tells me that c is equal to 0, and u2 is d times e power minus gamma r. You must have done all these things in your quantum mechanics course, but still let me revise. So, this is one part and this is other part. So, u has this functional dependence on r for r less than r naught, and u has this functional dependence on r when r is greater than r naught. Apply other things, the psi must be continuous everywhere. So, u must be continuous everywhere. So, you have expression for u in this region, expression for u in this region. At the boundary where both regions meet, at that boundary I can calculate u from this side or from that side, and that must be same, then it will be continuous. Okay. So, that means if I put r equal to r naught, these two expressions should give me the same value. U from the first expression at r naught should be equal to u from the second expression at r naught. U should be continuous. That means a sin k r naught should be equal to d e power minus gamma r naught. And similarly, slope must be continuous, du dr should be same. So, du dr if you do from here, it will be ka cosine k r naught. Differentiate and put r equal to r naught, and here also differentiate and put r equal to r naught. So, minus gamma d e to the power minus gamma r naught. This is coming from du dr is continuous. So, du dr from the first expression at r naught should be equal to du dr from the second expression at r naught. From here it is coming. Now, if you divide, what you get is k times cot k r naught. Divide, just divided by this, and this side it will be minus gamma. If you write in full, what was k? Tell me what was k? Square root of k. Cot k r naught, that means r naught into k. K is 2m v naught plus e over h cross square is equal to minus gamma. What was gamma? Okay. Now, in this equation I know R naught. How much it is? 2.1 femtometers. Range, which is roughly the radius of the deuteron. So, R naught is experiment. From experiments I know that R naught is this. E, from experiments I know how much is E? Minus 2.225 MeV. M, what is M? Mass of proton, mass of neutron divided by mass of proton plus mass of neutron. Reduced mass of this two. So, M is known, E is known, H cross is anyway known, R naught is known, this M is known, all right, this M is known, this E, E naught, E, just E. So, this E is, so everything is known except V naught. So, this is an equation in V naught. If you solve this equation, everything else is known. What will you get? V naught. This is a single equation in a single variable, one equation, one variable, solve it, right. So, one has to use computers and all those numerical solutions. It is not a quadratic equation that you use a formula to solve it, but in any way you have everything known except for V naught. So, you can get V naught from here, and that V naught turns out to be 36 MeV. So, now you have some idea of the strength of the potential, how strong is this nuclear interaction. Nucleon force is something like represented by a 36 mega electron volt deep potential well with a width of about 2 femtometer or so. So, this is the first approximation, first idea of how strong is nuclear force between two nucleons. Okay. Okay, we will start from here next lecture.